Hello, I'm Dr. Daniel Wilson, and welcome back to Lawrence Berkeley National Laboratory's free video course on laboratory testing of cookstoves. In today's lesson, we will be doing a walkthrough of Lawrence Berkeley National Lab's full cookstove testing setup. We will look at the equipment and procedures we've used to build a world-class cookstove testing laboratory. After watching this lesson, your lab will be able to incorporate a real-time fuel and water mass measurement system, design and operate a secondary dilution system, incorporate real-time aerosol measurements into the lab, and understand and implement an all-lab data acquisition system. In a prior video, we covered measurements of fuel and water. Most labs can cover their equipment needs with just one or two fuel and water scales that sit inside or outside the testing hood. These scales can measure fuel and water at the beginning and end of a test. However, our lab is interested in quantifying real-time consumption of fuel and real-time evaporation of water. To accomplish this, we monitor the mass of the entire cookstove setup, including stove, fuel, pot, and water in real time using a 45 kilogram capacity scale with a resolution of 0.1 gram. Before each test, we tare the scale with just the cookstove and empty pot on top. This means that any positive values read by the scale represent the weight of the water and the fuel in the cookstove. As the test is underway, the mass of fuel and water will decrease due to fuel consumption and water evaporation. To differentiate between mass loss of fuel and water, we perform what we call pot lifts at 5-minute intervals. During these pot lifts, we momentarily lift the pot long enough for the platform scale to register a reading. This value represents the weight of just the fuel. In order to estimate the weight of water at that same point in time, we can subtract the fuel weight from the combined weight of both the fuel and water taken immediately before the pot lift. Using linear interpolations, we can estimate the real-time fuel and water mass consumption over the course of the test. In addition to measuring real-time fuel and water mass, our laboratory has developed a real-time aerosol sampling system. This system has the capability of measuring real-time size-resolved concentrations of aerosols from 5 nanometers to 20 microns in diameter, along with black carbon and PM2.5 mass concentration. We developed this system to enable rapid cookstove design evaluations and to further our laboratory's research mission. From a cookstove design perspective, it is very useful to have real-time feedback about how changing cookstove performance parameters affect aerosol emissions. For example, if we are experimenting with forced draft cookstoves, we can change the flow rate or position of air jets and measure the changes in aerosol emissions in real time. From the research perspective, the capabilities of the system allow for deeper exploration about fundamental combustion mechanisms, potential health impacts of cookstoves, and information about how the aerosols will evolve in the indoor environment. Connecting real-time aerosol instruments to a cookstove testing system has several significant challenges. These challenges stem from the fact that the primary dilution tunnel can contain emission concentrations that are hundreds of times higher than the ranges the instruments were designed to measure. Almost all high-quality aerosol instruments were originally designed with the measurement of ambient air in mind. Therefore, these instruments will give poor data or could even be damaged if they are subjected to the extremely high concentrations of aerosols present in cookstove smoke. To reduce the concentration of emissions for the real-time instruments, we incorporate a secondary dilution system. As with the gravimetric system, we use an isokinetic sampling probe to sample emissions from the dilution tunnel. However, this sampling probe draws only about 1 liter per minute compared with the gravimetric system's 16.7 liters per minute. So, to maintain an isokinetic flow rate, the real-time sampling probe is smaller in diameter. To reduce the concentration of aerosols, we mix them with clean dilution air. The dilution air is supplied by a high-pressure bottle of purified air. This pure air contains no carbon dioxide or carbon monoxide, Then we run it through a HEPA filter to ensure it's aerosol-free. Note that we do not use pure nitrogen for sample dilution because we find that this can adversely affect the corona discharge of our fast mobility particle sizer. The flow of dilution air into our secondary dilution tunnel is metered by a mass flow controller. The sampled emissions and dilution air are mixed in a secondary dilution tunnel before being split off into various instruments. Guaranteeing full mixing in the secondary dilution tunnel follows the same design principles we outlined in the training about duct and primary dilution tunnel design. Remember from the aerosol sampling training that a cyclone must operate at a specified flow rate. In our lab, our real-time aerosol system uses the same model 16.7 liter per minute cyclone as our gravimetric system. Recall that our real-time aerosol sampling probe is designed to sample isokinetically at 1 liter per minute. So, to maintain the isokinetic sample and to maintain the dilution ratio stability, we want to keep this probe flow rate at a constant 1 liter per minute. Also, we have to maintain our cyclone flow rate at 16.7 liters per minute. This situation means that our dilution air must be supplied at a precise 15.7 liters per minute to balance these two required flow rates. However, that also means that our dilution ratio is fixed to only one choice, 16.7 to 1. If we want a higher dilution ratio, we cannot just put more flow through the dilution air mass flow controller. For example, if a very dirty stove required a secondary dilution ratio of 100 to 1, we couldn't just supply 99 liters per minute of air through the dilution air mass flow controller and hope for this to mix with 1 liter per minute of sample air. Remember, our cyclone must have 16.7 liters per minute of flow, and this flow is metered by the pumps in the aerosol instruments. So, if we were to force 99 liters per minute of dilution air into the secondary dilution system, what would end up happening is that we would push 82.3 liters per minute of clean dilution air out of the sampling probe. In order to accommodate dilution ratios higher than 16.7 to 1, we needed to incorporate a purge line before the cyclone. The flow rate through this purge line is controlled by a second mass flow controller designed to have its outlet connected to a pump. In this system, to achieve a 100 to 1 dilution ratio, we would supply 100 liters per minute of dilution air and purge 83.3 liters per minute. With 16.7 liters per minute of air being pulled through the cyclone by the aerosol instruments, 1 liter per minute of sample would have to enter the probe to balance the flows, and that would result in our 100 to 1 dilution ratio goal. Zooming out a bit, let's consider the diluted flow that will travel to the aerosol instruments. The 16.7 liters per minute through the cyclone is the sum of all the pump flows from the various aerosol instruments. However, these instruments' pumps vary slightly in their flow rates, and sometimes we may need to take an entire instrument offline. In order to ensure a constant 16.7 liter per minute flow rate through the cyclone, we incorporate a third and final mass flow controller to balance the flow through the cyclone. In between tests, we use a flow meter to check the flow through our real-time aerosol system cyclone and ensure that it's 16.7 liters per minute. If the flow is too fast or too slow, we adjust the flow through the third mass flow controller to achieve our 16.7 liter per minute goal. With all of these variables, we want to ensure that we have an accurate and stable dilution ratio. To do this, we use carbon dioxide as a tracer gas. Using a dedicated CO2 analyzer, we track the concentration of CO2 in the diluted emission stream. We compare the concentration in real time to the CO2 concentration in the duct measured using the gas sampling system discussed in a prior training. The real-time dilution ratio is simply the ratio of the real-time concentration of carbon dioxide in the duct to the concentration in the secondary dilution system. We use this real-time dilution ratio to back calculate the emission concentrations in the primary dilution tunnel. In total, We have 7 instruments sampling from the diluted emission stream. Each of these instruments measures a different property of the aerosol stream. In some, we are able to measure size-resolved particle concentrations in the diluted emission stream in size bins ranging from 5 to 20 microns in diameter. In addition, we measure the black carbon content of the emissions and approximate the real-time PM2.5 mass concentration. At each branch in the aerosol emission sampling lines, it's important to minimize particle loss by using a high-quality purpose-built aerosol stream splitter, sometimes called a Y. In our lab, we strive to have roughly equal flow rates through each branch of each Y in our lab. Some additional hardware is required to make this system work in our lab, including a dedicated PM1 cyclone for our fast mobility particle sizer and a third stage of dilution, this time with a capillary diluter to prevent coincidence errors just for our optical particle sizer. The individual operating principles, merits, and idiosyncrasies of each of our aerosol instruments is beyond the scope of this training, but you can find a comprehensive list of all of our laboratory equipment linked in the description of this video. Our full laboratory setup requires significant instrument control and coordination of many different data streams. In the past, we struggled to organize and coordinate all of the systems and data generated by our lab. To streamline this process, we've invested significant time and resources to build a custom graphical user interface to all the instruments in our lab. This interface, which we call the LBNL Cookstove Test Tracker, is written in Python and interfaces with all critical instruments in our lab. We can start and stop pumps, adjust flow rates, and most importantly, visualize and record data, all from one program. From a single screen, we record data on water and air temperature, gases, aerosols, and dilution ratios, while back calculating all important metrics that we're tracking. By coordinating all these data streams, we avoid a situation where we are forced to run a dozen or more pieces of special software all at once to control equipment and record data. A real-time view of all metrics for a cookstove test enables everything from fast, recursive design of cookstoves to more consistent fire tending. In conclusion, building an advanced cookstove lab requires significant investment in additional design and operation. However, if your lab is interested in the design of next-generation cookstoves or research into the fundamental mechanisms driving cookstove emissions and health impacts, a more advanced laboratory design may be necessary. To achieve the goals of your advanced lab, we hope that you consider incorporating a real-time fuel and water mass measurement system, designing and operating a secondary dilution system for aerosols, and incorporating a real-time aerosol measurement system into your lab. Finally, we hope you understand the benefits of and implement an all-lab data acquisition system. Thank you. I'm Dr. Daniel Wilson from Lawrence Berkeley National Lab. Please join us for our next instructional video on laboratory testing of cookstoves.